Hey everybody, welcome back. This is lesson 5 in our unit 3B, and today's lesson is called bond polarity. Now, in the last video, we talked about polyatomic ions, what they were, how they're formed, how to name them, and how to write the formulas. And today we're going to spend some time going on to bond polarity. And so the abbreviation we like to use is BEND, and we'll get into what that means shortly. So first, question for you. What do you think these images show? So take a second, look at it, and then add your response. So these pictures show the different types of bonds and really the electron distribution. So here we have something called a nonpolar covalent bond. And again, it's going to make more sense as we go on. But the electrons are being shared equally. Neither side is stronger than the other, neither side has more electrons. Here in B, we have a polar covalent bond, and here we have the electrons being shared unequally. So on this example, chlorine has 8 electrons around it. Hydrogen only has 2 electrons, so they're not being shared equally. And then C shows an ionic bond. It's that complete transfer. So you have two separate things. So when we talk about bond polarity, even just the word polarity or poles, you might think, oh, well, the North Pole or the South Pole, or magnets have North Poles and South Poles. And if we think about bonds, they also have two poles. But instead of North and South, they have a positive part and a negative part. And so we call that a dipole. So di means two, and pole. So you have two different poles, depending on their electronegativity. So this right here is the sign delta, and that's a positive. So this means, well, you would say this as delta positive, and this is delta negative. And what that means, it means it's partially negative, and this would be partially positive. Now, if you had full negative and full positive charges, that is your ionic bond. But in some of these bonds, some elements may hold on to the electrons more than others. And so the electrons with more electrons are kind of partially negative. So we'd say delta negative. And the way you can figure that out is the end. So END, or END, stands for electronegativity difference. And so this is super easy to calculate if you remember that electronegativity values are on table S. So you always do the larger electronegativity minus the smaller electronegativity. So if we have oxygen, oxygen's electronegativity is 3.44. Hydrogen is 2.2. Again, this is straight from table S. And so if you were to calculate the electronegativity difference for oxygen and hydrogen, you would get 1.24. That is that difference. Now that number will tell us something, and we'll get into that shortly. So try this now. Try doing the electronegativity difference between carbon and oxygen. So carbon has an electronegativity of 2.6. Oxygen has an electronegativity of 3.4. So you do 3.4 minus 2.6, and you get 0.8. So that would be your electronegativity difference for that. And so again, just a quick review on electronegativities. Its electronegativity defined is the want or the tendency to gain or attract electrons. So these nonmetals are going to be more electronegative than metals, but since we're talking just about nonmetals right now, table S has your values. So remember, this guy named Pauling decided to just give these values, and he said, oh, fluorine is the most electronegative, let's call that 4, and then everything else is less than that. Okay, so here is another great picture to kind of show electronegativity. The darkest color is the highest electronegativity value, and again, as you get closer to F, the darker and darker that purple gets. So if we're going to look at these electronegativity values, we can tell whether or not we have a polar covalent bond or a nonpolar covalent bond. So if we have a nonpolar covalent bond, this is equal sharing. So if you have nonpolar, there's no poles, there's no different sides. So everything is the same. And so in this picture, this is one of the pictures we saw at the beginning, everything is, the left side is the same size as the right side in terms of electron distribution. And generally speaking, things with an electronegativity difference, if you were to calculate it, between 0 and 0.4 are nonpolar covalent bonds. And so these are usually between identical atoms. So if you had H2, H and H, commonly you'll see C and C, you'll see CH. All of those are examples of nonpolar bonds. So why is CH a nonpolar bond? So you should have said carbon has an electronegativity of 2.6, H has an electronegativity of 2.2. So when you subtract that, you get 0.4. And so anything 0.4 or less is a nonpolar bond. And you can think of it as tug of war. You have two even sides pulling against each other. Now, oppositely speaking, you can have a polar covalent bond. And this is when one atom of the bond is stronger, has a stronger pull for the electrons. So here we can see that this side is smaller, this side is bigger. So this right side has that delta negative. Remember, that's delta negative. So that is the more electronegative element because it wants the electrons more on that side. So polar covalent bonds have an unequal sharing of electrons. And so generally speaking, if you were to calculate the electronegativity difference, you get anything between 0.5 and 1.7. You might also see it as 0.5 to 2. There are a few examples that go beyond 1.7, so you just have to check. So again, in a polar covalent bond, one side is slightly negative because it has more electrons around it, and then one side is less electronegative. So if you were to draw, let's say, a dot diagram, we have H and Cl. Here you can see that the electrons, oops, Cl, not C, Cl, all the electrons are surrounded around Cl. So here would be that delta negative, here would be that delta positive. If we were to go back and draw, let's say, a dot structure for here, if we have Cl and Cl, both sides have the same number of electrons around it, so it is nonpolar. So drawing these dot structures is, or just having those ideas in your head, makes this a little bit easier. So if you were to look at a picture, you could be able to tell which is polar and which is nonpolar. And so that's why drawing your lone pair electrons is super important. So here's a kind of number line to help you out. Anything from 0 to about 2 is a covalent bond. And then if you were to further classify that covalent bond, things between 0 and 0.4 are your nonpolar bonds. Between 0.4 and about 2, those are your polar covalent bonds. Again, the most important thing to remember covalent bonds is a nonmetal and a nonmetal, and ionic is a metal and a nonmetal. So your first step should be checking what kind of elements you have, because that helps you when you're in this kind of weird situation between 1.7 and 2. So here is a flowchart. We're going to work on it together to determine the type of bond. So your first step should be to look at what elements you have. And if you have a metal and a nonmetal, that is an ionic bond. You're done. You don't need to calculate any electronegativity difference. That's it. Metal, nonmetal, always going to be ionic. But if you have a nonmetal and a nonmetal, that is covalent. But sometimes Sometimes the question will be like, well, is it polar covalent? Is it nonpolar covalent? So then you have to look at the electronegativity differences. So if the electronegativity difference, or the end, is smaller or less than or equal to 0.4, that is your polar covalent, nonpolar covalent rather, sorry. So less than 0.4 or smaller, you're nonpolar covalent. If you have an electronegativity difference that is bigger than 0.4, and again, you still have metals and nonmetals, that is your polar covalent. So covalent. So really this comes down to calculating the electronegativity difference. So here is, a great kind of flowchart to help you out. So that's pretty much it. Next time we will talk about molecular polarity. But before we can do that, we really need to make sure that bond polarity makes sense, because molecular polarity takes into account the entire thing. So on that note, that is it. Have a wonderful day. Bye.